An efficient network coding-based error index for queries in road networks. Abstract wireless broadcast is an efficient strategy for disseminating data to the clients in road networks. Network partition index, NPI, doesn't address how to handle various data objects or increased to a large number in broadcast system and link errors. To address these problems, an NPI-based error index, called Network Coding-Based Spatial Error Index, NCSI, has been proposed by using hybrid broadcast, HB, scheduling and adaptive XOR-based network coding for spatial queries in road networks. We conducted various experiments for evaluating query performance. The experimental results show that NCSI has better query performance compared with state-of-the-art NPI. Keywords: wireless broadcast, network coding-based spatial error index, hybrid broadcast, adaptive XOR-based network coding, spatial queries, road networks. 1. Introduction. Due to rapid advances in both wireless communication and mobile computing, location-based services are more useful to the clients in real-time and day-to-day applications. Recently, most of the GPS, i.e., Geographical Positioning System, enabled devices such as smartphones, laptops and PDAs request nearest information via spatial queries in road networks. The road network has been modeled into time-independent and time-dependent and computed traveling time based on the distance and traffic in a network respectively. However, these models have been suffered from scalability and security 1, 2, 3, 4. To address these issues, wireless broadcast strategy has been adopted. 5. Wireless broadcast strategies are classified into push-based, pull-based, and hybrid scheduling. However, these strategies have been suffered from sequential data access 6, 7. More research has been done on query processing in Euclidean space rather than road networks 8, 9. However, in most of the real-time applications, query processing in road networks is essential. Error index adopted for shortest path queries in a road network and doesn't address range queries and KNN queries 10. Recently, NPI-based error index adopted for various spatial queries in road networks. However, NPI doesn't address well scheduling strategy when the data objects are increased to a large number in broadcast system and link errors 11. To address these problems, we propose NCSI using HB scheduling and adaptive XOR-based network coding for spatial queries in road networks and improve query performance. The overall idea of this work is explained as follows. The original road networks may contain various data objects such as restaurants, shopping malls, hospitals, gas stations and schools etc., and these are classified into two data sets, namely general and specific based on client's requirement, and computed cutoff point 12. Using grid partition strategy, road network is partitioned into small grid cells, and pre-computed some general information such as diameter of each cell and minimum/maximum network distance between every pair of cells that will be carried by NCSI. At server site, we incorporate adaptive XOR-based network coding into broadcast scheduling program, and broadcast general and specific data objects of NCSI with network connectivity information of each cell using HB scheduling. On the client site, once a client receives a query request from a mobile user, then it searches query result in its cache. If found, then it return the result. If not found, then the client tunes into channel, retrieves required information and decode the data. Finally, process the query using Dijkstra's shortest path algorithm. If required data doesn't broadcast while tuning, then the client send query request to server via pull-based scheduling. While broadcasting, if any free time slots exist, then server broadcast encoded form of client's requested data objects, i.e., specific data objects, along with general data objects based on longest waiting time in the queue on priority order, and updates optimal cutoff point. The contribution of this paper can be summarized as follows. Propose NCSI using HB scheduling and adaptive XOR-based network coding for spatial queries in a road networks. Propose search algorithms at client site, which includes range query, k-nearest neighbor query and continuous k-nearest neighbor query. Experiments are conducted using real road networks data and compared the performance of NCSI with state-of-the-art UNPI. The rest of this paper is organized as follows. Section 2 describes brief overview and previous works of both wireless broadcast and network coding. Section 3 presents XI broadcast strategy for spatial queries in road networks. Section 4 discuss various searching algorithms. Section 5 reports performance evolution, and Section 6 concludes the research paper. 2 related works. 2.1 Wireless data broadcast. Wireless broadcast is an efficient strategy for disseminating various data objects to clients via wireless channel. Various interleaving strategies has been adopted for disseminating AIR index data to clients. Among these, 1. Data interleaving strategy widely used in wireless environments is shown in Fig.1. In this strategy, data is divides into equal data segments and broadcast each data segment preceded by AIR index via wireless channel 5. For evaluating performance, 1. Data interleaving strategy has been used 2 performance parameters, and these are tuning time and access latency. Tuning time defined as amount of time spent by a client tune into channel and retrieves required data. Access latency defined as amount of time spent by a client to submission of a query and gets query result. 2.2 Query processing in wireless broadcast environment. In wireless broadcast environment, various indexing structures such as R*tree, dtree, grid index, Hilbert curve index, HCI, and broadcast grid index, BGI, are adopted for processing spatial queries in Euclidean space 13, 14, 15, 16, 17. However, these indexing structures are not suitable for spatial queries in road networks. In road networks, AIR indexing structures has been adopted for spatial queries and supports only shortest path queries 18, 19. 2.3 Network coding. In wireless environment, while disseminating data to clients, some of the data is lost due to unreliable nature of wireless links. In order to address this problem, automatic repeat request, ARQ, has been adopted. In ARQ, after each transmission, clients send feedback information to the server, be it a positive or negative acknowledgement. However, ARQ is not efficient if there is an increase in the size of the network. The alternative strategy to address this problem is referred as forward error control with channel coding, in which the server broadcasts coded packets, i.e., data packets are coded using network coding schemes, to clients, and then clients perform decoding on coded packets and conclusively get the original data packets. The noteworthy advantages of this strategy are scalability and throughput improvements and robustness of the networks. Network coding has been widely used in wireless multicast environment for improving query performance. Network coding has been primarily introduced for improving performance in multicast routing 20. Network coding is regarded a general strategy in packet routing that allows an intermediate router to encode an outgoing packet by mixing multiple incoming packets appropriately. In a multi-hop wireless network, to meet unicast demands, game theoretic framework is introduced using network coding 21. A cross-layer optimization framework is formulated to derive the maximum throughput for multicast traffic. In a random network, the optimization strategy considers network coding in network layer and conflict-free transmission schedules in MAC layer 22. In a wireless network, one-hop opportunistic network coding is adopted and argued for making rate control and scheduling network coding aware 23. The server disseminates a set of data blocks over a broadcast channel to a set of caching clients called index coding problem 24. The index coding problem is motivated by various applications in wireless networking and distributed computing 25. For instance, one can find such applications in satellite communication networks where the clients have limited storage and limited maintenance of the received information. Efficient index codes are useful for the wireless network architectures that utilize the network coding and opportunistic listening techniques 26. Feedback-based adaptive network coding schemes are designed for minimizing decoding delay in each transmission of the packet-based erasure networks 27. All traditional scheduling algorithms in data broadcast are based on the assumption that only clients requesting the same data item can be satisfied in one broadcast tick. Coding problem is adopted in on-demand broadcast for reducing accessing time. In this approach, each broadcast data item is encoded from at most 2 data items and doesn't fully utilize the advantages of data broadcast encoding 28. However, it is found in this approach that no restriction is considered on the number of encoded data items 29, 33, 34. Approaching differently in a proposed framework where in a grid cell, availability of data objects in each adjacency cell can be encoded, and as such it is a significant factor by which different performance objectives can be achieved. 3. Network coding-based spatial error index for queries. In road networks, NXI is very useful in wireless broadcast environment for processing spatial queries in road networks as it derives the advantages of network coding. Based on the study VIDE 11, the partition of the road networks into small grid cells, computing of the diameter of cell and border point, and formation of NXI is shown below in Fig.2. Furthermore, this section describes 1. Data segment, 2. Adaptive XOR-based network coding, and 3. NXI broadcasting method on wireless channel. 3.1 Data segment. Broadcast program contains 2 major components. They are error index and data. An error index represents NXI and data represents data objects respectively. In this work, let us assume that structure of road network is captured by adjacency lists, and each client has unique ID, i.e. identification. From the Fig.2, the grid cell C2 contains 3 clients, i.e., V1, V3 and V4, and 2 data objects O3 and O4 respectively. In this cell, the adjacency lists of all the vertices are broadcast based on the order of the client's IDs. For example, consider the structure of V1 adjacency list. It contains 2 neighbors V3 and V4, and each neighbor is represented by 4 tuples, i.e., V3, 1, 1, 04, where the first field V3 indicates adjacent node, i.e. V3 connected to V1, the second field 1 indicates a weight of an edge, V1, V3, the third field 1 indicates the number of data objects lying on this edge, and the fourth field is a pointer which points to the first data object on this edge. If there is no object on this edge, the pointer is set to null. The overall structure of grid cell C2 is shown in Fig.3. 3.2 Adaptive XOR-based network coding. In grid cell C2, we should consider the structure of V1 adjacency list. It contains 2 neighbors V3 and V4. V1 to V3 contains data object O4 and V1 to V4 contains data object O3. For example, V1 to V3 contains 1 or more than 1 data objects, then these data objects are encoded using adaptive XOR-based network coding and broadcast. At client site, decoding takes place. NPI doesn't satisfy multiple client requests in a single tick as network coding concept has not been used. NXI, being a more flexible concept, satisfies multiple client requests in a single tick using adaptive XOR-based network coding. The salient features of the concept are stated here. 1. Adaptive XOR-based network coding is a simple one with fewer overheads. 2. Server should know what type of data objects are being requested by clients as well as the client's cached data. 3. In a grid cell, based on the availability of data objects in a adjacency cell, data objects are encoded using adaptive XOR-based network coding and broadcast by the server. And 4. Server and client's site use simple XOR operation for encoding and decoding the data. 3.3 How to broadcast NXI with data segment on wireless channel. The server broadcasts NXI with data segment via wireless channel using 1. Data interleaving strategy. Then the interested client tunes into channel, retrieve the data and decode it. 4. Processing of spatial queries at client site using NXI. This section describes various searching algorithms at client site which include range query, k-nearest neighbor query, and continuous k-nearest neighbor query. The objective of these algorithms is to process the query efficiently and return result to the client with the help of NXI. For processing queries in road networks, Dijkstra's shortest path algorithm has been followed because it is simple and efficient for small subgraph retrieved and decoded by clients. In this task, it is assumed that the client's locations are located at network nodes and easily extended to support the case where the client's locations are put up along the network edges. 4, 18, 19. 4.1 Range Query. In road networks, range query retrieves all data objects within a network distance d from a query point Q, and it is denoted as Q, D, S, equals OO. S. O, Q equals D, where Q is a query point, O is a data object, D is a network distance and S is a dataset in road networks. %receive_query, a client waits for receiving a query from the mobile user, perform encoding and decoding at server and client sites respectively using XOR-based network coding, T-time, CQ valid grid cells from a query point Q, RQ valid range query result from a query point Q, AQI minimum or maximum network distance from a query point Q, retrieve index header, the client retrieves index header, sleep until cell broadcast, client sleeps until required data broadcast, retrieve cell. Client retrieves the cells containing query result, adjacency lists. Adjacency lists are forms as subgraph, Dijkstra, subgraph, Q, D. Process the query using Dijkstra's shortest path algorithm and return query result, compute a cutoff point CP using 12%. Perform encoding and decoding at server and client sites respectively using adaptive XOR network coding %. In the light of the above-mentioned algorithm, it may be assumed that the client being located at node V5 requests range query to find 4 restaurants from query point Q with network distance D equals 3. Then the range query result obtained is O1, O2, O3, and O4. 4.2 K-nearest neighbor query. K-nearest neighbor query defined as a mobile client retrieves K-nearest data objects from a query point Q. Like a range query, the range is not fixed in a K-nearest neighbor query and it will be depend on the value of K and location of query point Q. In this work, we estimate network distance max based on XI in order to find candidate cells. Once max is estimated, then K-nearest neighbor query is converted into range query and retrieve candidate data objects within a network distance max from a query point Q. The max is estimated based on the upper bounds of network distance between any object in CU and any objects in CV and denoted as UB, CU, CV. Lemma, given two cells CU and CV, the network distance between any object U in CU and any object V in CV is bounded by diameter, CU, plus diameter, CV, plus SUV, and it is denoted as UB, CU CV, equals diameter, CU, plus diameter, CV, plus SUV. Based on above lemma, the max is estimated as follows. For example, a query point Q is located in cell CQ, we access CI based on Thenon descending order of AQI, that is CI is visited earlier than CJ if AQI AQJ there is tie, UB, CQCI and UB, CQCJ, are used as tiebreaker and one with smaller UB value will be visited first. In this process two parameters are used, one is count, i.e., the total number of data objects in all the cells visited so far, and the other is UB, the max, for each visited cell CI. We calculate UB, CQCI and set UB, the max, to the maximum UB, CQCI, found so far, and meanwhile we check CI, and update count. This process is continuing until count reaches to value K. Input, Q, query point, K an integer, S, data set. Output, valid K-nearest data objects from query point Q. %receive_query, a client waits for receiving a query from the mobile user, perform data encoding and decoding at server and client sites respectively using XOR-based network coding, T-time, CQ valid grid cells from a query point Q, RQ valid range query result from a query point Q, AQI minimum or maximum network distance from a query point Q, QQ, candidates cells from a query point Q, retrieve index header, client retrieves index header, range query, Q, UB, the max, S. Process the range query and return subgraph with candidate cells, Dijkstra, subgraph, Canc, Q, K, Process the query using Dijkstra's shortest path algorithm and return query result. Compute a cutoff point CP using 12%. Perform encoding and decoding at server and client sites respectively using adaptive XOR network coding %. Based on the above cited algorithm, it may be assumed that the client is located at node v5 and requests k-nearest neighbor query to find 4 nearest neighbor restaurants from a query point Q. Then k-nearest neighbor query result is 01, 02, 03, and 04. 4.3 Continuous k-nearest neighbor query. Continuous k-nearest neighbor, CKNN, 30, 31 query widely used in many real-time applications. For example, mobile user continuously sends a query request to other mobile users while moving on the road networks called CKNN query. In CKNN query, once a client receives query from a mobile user, then it initially finds its located grid cell and the query path, V1, V2, VL. That's why, based on the query path, the client can find data objects in each segment in road network. Each segment in the network is called as valid interval, and all valid intervals contain start/end points, and these points are called as split points. Let us assume that if a client located in the same safe region requests the KNN query, the obtained result is the same as the partial road network is the same. So unless the client tunes into another channel and retrieves a new candidate's cell leaving the current safe region with maximum distance, the condition, Q1 equals, UB, max, DK/2, goes unsatisfied. Algorithm 3, Space Validation for CKNN query. Input, a query path P, V1 V2, VL. Output, valid space segments, VSS1, VSS2, VSSL. %receive_query, a client waits for receiving a query from the mobile user, perform data encoding and decoding at server and client sites respectively using XOR-based network coding, T-time, CQ valid grid cells from a query point Q, RQ valid range query result from a query point Q, AQI minimum or maximum network distance from a query point Q, starting point, L ending point, V starting vertex, N and I integer, G1 valid query path, G11 query path from starting point to ending point, P path, V start 6, UB, max, DK/2. If the condition is true, then client need to tune into channel and retrieve new candidate cells, VSSN, V start, 6-1, valid space segments from V start to 6-1. Compute a cutoff point CP using 12%. According to the above cited algorithmic study, it may be assumed that the client is located at node V5 and requests continuous k-nearest neighbor query to find continuous 4 nearest neighbor restaurants from a query point Q. Then the ascertained continuous k-nearest neighbor query result is 01, 02, 03, and 04. 5. Performance evaluations. Experiments have been conducted for evaluating query performance using NS2 simulator with Windows 7 platform, 2.33G Intel Core 2 CPU and 3.2 GB RAM. 5.1 Experimental process. In this simulation, real road networks data set, namely Oldenburg, OL, and California, CAL, have been considered. The OL contains 6,105 nodes and 7,035 edges, and CAL contains 21,048 nodes and 21,693 edges, 32 respectively. The evaluation is run on simulator which contains server, broadcast channel, and clients. For simulating results, 100 clients and 500 random queries are used. In this work, we cared that 1. The size of data object is fixed at 128 bytes, 2. A set of data objects are randomly generated and uniformly distributed, 3. Query issuing points are always at the network nodes, 4. Network bandwidth is dynamic, 5. Tuning time and access latency are measured in terms of number of bytes of data transferred in a wireless channel. 5.2 Cycle length. Cycle length plays an important role in this simulation because it has directly impacts on the access latency. The original road network is partitioning into 2i times 2i uniform grid cells, where I vary from 0 to 4, i.e., the number of grids ranges from 1 to 4 to 16 to 64 and to 256. The number of grid cells in a network is set to 4i and mapped into Hilbert curve order. The server disseminates data using 1. M strategy by setting M to its optimal value 5. We compared the performance of NXI with state-of-the-art NPI based on grid sizes 42, 43, and 44 respectively, and these are denoted as NXI/NPI 16, NXI/NPI 64 and NXI/NPI 256. Table 1. Parameter settings. 5.3 Range query. In a range query, a mobile client is located at query point Q and issue a query with distance d, then it retrieves all data objects within a d distance. In this simulation, we ignore an object density dn but fixed at 0.1 because more number of data objects will not affect on query performance, and the radius of range query is varied from 0.01 dn, to 0.05 dn, to 0.1 dn and to 0.2 dn. From Fig.5, we observe that with smaller radius, NXI 16 and NXI 64 have better tuning time compared to state-of-the-art NPI 16 and NPI 64 respectively. As for the access latency, NXI 16 has shorter access latency than NPI 16 consistently. Similarly, NXI 64 also has smaller access latency than NPI 64 in some cases because NXI has used both XOR-based network coding and cache at server and client sites respectively. This set of experiments gives a comparison between the performance of NXI 16 and NXI 64. NXI 16 has smaller index size, so the cycle is shorter, hence access latency is smaller. Similarly, NXI 64 has narrow grid cells, which provides tighter upper bound, hence smaller search space for range query, resulting in shorter tuning time. By observing range query experimental results, NXI 64 expected to produce a better system performance compared to NXI 16. 1.jpg. Fig.5 Performance of range queries with radius. 5.4 K nearest neighbor query. We evaluate the performance of state-of-the-art and proposed algorithms under various K values, as presented in Fig.11. In this experiment, objects density is fixed at 0.1 and K values are varied from 1, to 5, to 10, to 15. We consider only small K values in our experiments because mobile devices have small screen, and difficult to display a large number of NNs. We observe the performance of tuning time presented in Fig.6, A, and Fig.6, C. NXI 256 has better tuning time compared to state-of-the-art NPI 256, because it used pre-computation information carried by NXI and cache data at clients enables the clients to prune the search space effectively. But, for the KNN queries with K1, tuning time of NXI increases as K becomes larger. Because the upper bound of the distance between the query point and KTHNN is enlarged by K, so the clients would process range query with larger radius. However, even under a relatively large K, the tuning time of NXI is still smaller compared to state-of-the-art NPI. We also observe the access latency presented in Fig.6. B, and Fig.6, D. NXI 16 has outperformed because of small index size. Similarly, NXI 64 also has better performance compared to state-of-the-art NPI 64. However, NXI 256 has energy efficient, but it has large access latency because of larger index size. We also evaluate performance of different index with various object densities as shown in Fig.7. For simplifying the comparison, we assume that the number of grid cells is fixed at 64 for both state-of-the-art NPI and NXI. The performance of NXI 64 is more stable to the variation of the object density compared to state-of-the-art NPI 64 because NXI enables the clients to check the number of objects in each grid cells and compute the upper bound of the distance of the KTHNN. When the object density becomes dense, then the upper bound decreases because it prunes away more unnecessary grid cells. 5 CKNN query. In CKNN query, query path length ratio, QPLR, is defined as the ratio of the query path length to the diameter of the road network. The query path is generated by the shortest path between two randomly selected nodes in the network. In this experiment, object density is fixed at 0.1 and QPLR ranges from 0.01 to 0.2. The performance for the OL and CAL data sets for answering CNN queries with K equals 10 is shown in Fig. 8. The tuning time of XI64 varies as QPLR changes because it enables space pruning. However, tuning time of XI64 has better than state-of-the-art NPI64. But XI64 has suffered from longer access latency because the CKNN algorithm under XI index allows the clients to tune into the channel to update the partial road network and KNN candidates only when they arrive at the first point of a new SVS. We also evaluate the performance of state-of-the-art NPI64 and XI64 for supporting CNN queries with different K values. In this experiment, we fixed QPLR at 0.1, K is varying from 1 to 15, and object density is fixed at 0.1 for both OL and CAL shown in Fig. 9. XI64 has more energy efficient compared to state-of-the-art NPI64 for different K because the pre-computation by XI helps to clients prune the needless regions and avoid the clients keeping tuning into the channel rapidly as the clients move to a new position. However, access latency of XI64 has better than state-of-the-art NPI64 with different K. 6. Conclusion. In wireless mobile environments, spatial query processing is a challenging issue due to the following limitations such as low bandwidth, limited energy and capacity, and mobility. In this work, we observed that XI has improved query performance compared with state-of-the-art NPI because XI effectively utilized the advantages of network coding and cached data at clients. In future, we can extend this work by incorporating in advanced network coding strategies and spatial queries.